Welcome to my final capstone presentation. My name is Jarvis Gadinga Tekapa, and this presentation is the culmination of my capstone project for Data 670. My project explores how data analytics and machine learning can be applied to predict mental health treatment seeking behavior in the tech industry. I will walk you through the project scope, data sources, key techniques, model development, findings, and recommendations for future analysis. The goal is not just to present results, but also to tell a compelling story backed by analytics. Let's get started. Project scope and objectives. The tech industry continues to struggle with mental health stigma, inconsistent access to care, and limited early detection mechanisms. This project aims to predict whether employees in tech environments are likely to seek mental health treatment using both employee level and employer level data. The key predictors include personal history, work conditions, and organizational support structures. Addressing this challenge requires not just statistical rigor, but also sensitivity to ethical concerns and fairness. We focus on making predictions that could inform HR interventions and wellness program design. This scope was chosen because of its real-world relevance and potential impact on workplace well-being. Data sources. We use two datasets, the OSMI Mental Health in Tech Survey from Kangar and the CDC's Workplace Health in America Survey. The OSMI dataset provided individual-level responses, while the CDC dataset offered employer-level wellness support metrics. The two were integrated using a derived feature called company size category to align employee perspective with organizational policies. Both datasets require extensive cleaning, normalizations, and transformation. Techniques included regular expressions mapping, categorical consolidation, and range standardization. This integration enabled a more comprehensive analysis of mental health behaviors across organizational scales. Data preparation and cleansing. The dataset was prepared using SAS Enterprise Miner, Python, Excel, and Tableau. In Python, we handled missing values, corrected inconsistent entries, and recorded categorical variables such as gender. We also implemented threshold-based filtering for outliers in age and other fields. In SAS, stat exploit and graph exploit help in variable profiling and inform future selection. The final dataset included engineered fields like company size category and standardized responses for gender and work interference. Tableau was used for visual inspection to confirm consistency across both datasets. Exploratory visualizations. We developed several key visualizations in Tableau. One chart compared treatment-seeking behavior between remote and non-remote workers. Another showed the impact of wellness program on work interference, revealing that access to wellness support correlates with reduced interference. A third visualization broke down treatment rates across company sizes, highlighting that employees at smaller firms may face fewer barriers to seeking help. These visual insights guided future prioritizations in model development. They also supported deeper explorations into the contextual effect of organizational structure and policy. Predictive models used. Three predictive models were developed using SAS Enterprise Miner: Logistic regression, decision tree, and gradient boosting. Each model was trained using a stratified 70/30 train validation split. Due to class imbalance, we lowered the classification threshold to zero point 0.3 to improve sensitivity. We evaluated performance based on area under the curve, recall, precision, F1 score, and misclassification rate. Each model had its own strength: logistic regression for interpretability, decision trees for rule-based logic, and gradient boosting for high predictive power. Let's take a look at the performance of each. Logistic regression results. The logistic regression model performed well with an area under the curve of 0.81. It achieved 74.9% accuracy, 80.1% recall, and a precision of 72.86% on the validation set. Key predictors included work interference, family history, and mental health benefits. This model offered clear coefficient interpretations, which made it useful for explaining decisions to stakeholders. While it lacked the ability to capture complex interactions, it provided a strong baseline and influenced later model developments. Its transparency was a major advantage. Decision tree results. The decision tree model enhanced interpretability with a visual logic flow. It achieved a recall of 89.5% and an F1 score of 78.10% on the validation set. The model split first on family history, followed by work interference and care options. This clearly demonstrated the interactions between personal and workplace factors. While the precision was slightly lower than logistic regression, the tree structure allowed actionable policy insights. It was particularly useful for scenario-based HR planning. Gradient boosting results. The gradient boosting model delivered the best overall performance. It achieved 76.52% accuracy, 83.25% recall, and an F1 score of 78.16%. Unlike the previous models, it captured intricate nonlinear interactions. Predictors like company size and remote work became more important when combined with other features. Although less interpretable, the model's sensitivity made it ideal for identifying at-risk individuals. Its generalizability and robustness made it the best candidate for deployment. Model comparison table. This table summarizes model performances. Gradient boosting outperformed the others across nearly all key metrics. Logistic regression offered the best interpretability, and decision tree provided transparency with visual logic. However, gradient boosting achieved the highest area under the curve of 0.82, an F1 score of 78.16%, making it the champion model. It also minimized false negative, a crucial factor in healthcare and wellness analytics. The choice was made based on both performance and operational potential. Insights and takeaways. Key findings include the predictive power of work interference and family history. Company level variables like wellness support and size also had meaningful effects. The analysis confirmed that predicting treatment seeking behavior requires both personal and organizational context. One major lesson was the importance of threshold tuning to manage class imbalance. Another was the need for fairness aware design. especially when dealing with sensitive features like gender. Finally, we learned that stakeholders' communication must be balanced with analytical complexity. Recommendations and future work. For future analysis, I recommend testing more advanced ensemble methods like XGBoost and incorporating external mental health indices. Real-time dashboards and automated flagging tools could also be developed for HR use. Future versions should include fairness audits to ensure predictions are equitable across demographics. Additionally, longitudinal tracking could help evaluate long-term impact of wellness initiatives. From a modeling perspective, expanding the feature set to include job role, tenure, or location might improve precision. Overall, the project lays a strong foundation for both academic research and practical applications. Project success factors. On this slide, I would like to highlight four key factors that contributed to the success of the project. First, we successfully met the core objective of the project, building predictive models to estimate the likelihood of mental health treatment-seeking behavior among tech workers. This involved designing, training, and validating multiple models, including logistic regression, decision tree, and gradient boosting. Second, we ensured that our insights were HR friendly and actionable. Visualizations were created to communicate trends clearly, such as the impact of work interference, company size, and access to mental health benefits. This helped bridge the gap between data science and organizational decision making. Third, the model developed were not just accurate but also generalizable across both training and validation sets. We maintain strong performance matrices including recall, precision, and area under the curve. This gave confidence that the models could be applied in real-world workplace wellness initiatives without overfitting. Finally, the project laid a strong foundation for future analytics in workplace mental health. From the insights gained, we can build more complex pipelines, introduce fairness auditing, and even integrate real-time data or natural language processing-based analysis in the future. Thank you for your time and attention. This project was both technical and emotional journey into how we use data science to support mental health in high pressure environments like tech. I'm happy to answer any questions about the model, data, or methodology. Your feedback is welcome and I look forward to hearing your thoughts.